Good morning, everybody. So this is our second day of Argonne 5th quantum computing tutorial. My name is Yuri Alexeev. I'm an organizer of this tutorial. And today is today's speaker is going to be Dmitry Fedorov, who is a postdoctoral fellow here at Argonne National Lab, and he is our expert in development of quantum algorithms to solve quantum chemistry problems. I want to remind everybody that we're going to have a following format for these presentations. So in the first hour, Dmitry will give a presentation. As this is going to be just theoretical introduction, it will take roughly 1 hour. I suggest everybody to collect all the questions and ask all of them in the second part. So at 11 a.m. roughly, Dmitry will start the hands-on session, and that will be a good time actually to ask Dmitry any questions about his presentation. For the second part, you'll need to have IBM Q account and also download the file from Jupyter Notebook from GitHub, but Dmitry will cover it. Dmitry, it's all yours.
All right, thank you, Yuri, for introduction. I'm going to share my screen. Can you see and hear me okay?
Yeah, everything is fine, thanks.
All right. So today I'm going to talk about variational quantum eigensolver and how we use it to solve the quantum chemistry problems. So first of all, a quick outline of my talk. I'll give you a brief introduction on quantum algorithms in general and how they're different from the classical algorithms. Then I will talk about the electronic structure problem, where does it come from and how it's solved on the classical computers. And then I'll talk about simulation of quantum systems on quantum computers. And then we'll get to the actual variational quantum eigensolver, which involves the following parts, where we map the Hamiltonian from classical to a quantum computer. And we have the quantum classical loop for finding eigenvalues of that Hamiltonian. We parameterize the wave function to represent it on a quantum computer. And in the end, I'll talk about the main VQE achievements and challenges. So first of all, quantum algorithms are not just algorithms that solve classical problems faster. And quantum computer is not just a computer that can do the same stuff as classical computer, just faster. It is based on principles such as superposition and entanglement, which are quantum principles, and your algorithms need to take advantage of that. And what people are talking about nowadays is the quantum supremacy or quantum advantage, where you basically get, for a certain problem, you get speed up compared to the classical algorithms. And so some of the examples are of fully quantum algorithms as famous Shor's algorithm that for prime number factorization, that is if you have basically a good quantum computer, you can factorize very large numbers, which are used in modern encryption. And that's one of the possible applications when we do have a large and capable quantum computer. Another example is the HHL algorithm for solving linear systems of equations, Grover's algorithm for database search, and sort of more relevant to the talk today is the quantum phase estimation, which finds eigenvalues of unitary operators. And Hamiltonian is a unitary operator, and we potentially can use this algorithm in the future to solve quantum chemical problems exponentially faster. And then there is hybrid quantum classical algorithms such as QAOA that you're going to learn about later this week for optimization problems, and the variational quantum eigensolver that I'm going to talk about today. But before we go into the quantum world, I'll give you a brief introduction to the electronic structure problem, for those of you who are not familiar. And we begin with the time-independent Schrödinger equation, where we have our Hamiltonian H, the molecular wave function psi, and E represent the eigenvalues of this Hamiltonian. And as you probably know, the Hamiltonian is sum of the kinetic energy and potential energy terms. So in this equation, you have kinetic energy of the nuclei, kinetic energy of electrons, interaction of electrons with the nuclei, the potential energy of interaction of the nuclei, and the potential energy of interaction of the electrons. And in most of the applications, we employ the Born-Oppenheimer approximation, which allows us to separate electronic and nuclear motions due to the fact that nuclei move much slower than the electrons. And that allows us to do this factorization of the molecular wave function into electronic wave function and the nuclear wave function. And within this approximation, we can neglect the kinetic energy of the nuclei and the potential energy of the interaction of the nuclei is a constant which can be easily computed and just added in the end. And so what we're mostly doing in quantum chemistry is solving the finding eigenvalues of the electronic Hamiltonian. That's over here. And the eigenvalues of the Hamiltonian, when we calculate it for different geometries of the molecule, give us the potential energy surface that can be used then to describe the nuclear motion on these potential energy surfaces. And so this equation cannot be solved exactly for anything larger than the hydrogen or hydrogen-like atoms, and we use approximate solutions to do this on classical computers, and that's one of the main sort of problems in quantum chemistry. Before we go further, I'll quickly mention the chemical accuracy. Basically, how close do we need to be to the real solution when we solve these quantum chemistry problems? And it's useful to think of it, say we have some reaction where we start from the start. To get from the start to finish, we need to overcome some reaction barrier or activation energy. And using this simple reaction rate law, we can estimate that so here K is the reaction rate and delta E is the activation energy, and here's the temperature and the constants. And basically to get to the, in terms of reaction rate, to get to the accuracy of roughly within 10 times in terms of reaction rate, our energy barrier needs to be computed with the accuracy of 1 kilocalorie per mole. And that's sort of the number that is used in quantum chemistry to think in terms of how accurate the result is. And how do we represent the electronic wave function in our calculations? There are various ways to do that, but probably the most common and the one that I'll be talking about today is the where the wave function represented by the Gaussian basis functions, where basically each atom has some number of Gaussian functions centered on atoms, and the so-called molecular orbitals are linear combinations of these atomic Gaussian basis functions. And to account for Pauli exclusion principle, we have this structure called the Slater determinant that basically accounts for make sure that the electrons obey Pauli exclusion principle, and our wave function, electronic wave functions, is anti-symmetric. All right, so as I already said, we are solving electronic time-independent Schrödinger equation for electrons, and the first step that one commonly takes is the get a solution, Hartree-Fock solution, which is basically a mean field treatment of the problem where each electron moves in a field created by all other electrons, and the solution gives you the Hartree-Fock energy. And so in this diagram here, the blue bars are basically the molecular orbitals, and up and down arrows are electrons with spin up or spin down. And the orbitals that are occupied in Hartree-Fock I'll refer to as occupied, and the virtual orbitals are unoccupied orbitals. And basically, when we talk about the higher quality solution in quantum chemical problems, we need to include not just the Hartree-Fock electron configuration, but also electron configurations where some of the electrons excited from the Hartree-Fock configuration. And this energy difference between the true value and the Hartree-Fock energy is the correlation energy, which is usually rather small, but very crucial for the chemistry of the system. And the methods that allow you to include these configurations are, some of them are coupled cluster, configuration interaction, various multi-configurational methods, and the full configuration interaction, which considers all possible configurations and provide exact solution for a given basis set. And it would be great if we could actually do that, but as you can tell, the number of possible configurations increases exponentially. And obviously, you quickly get into the threshold of the computer capabilities with the exponential growth of the number of configurations. And so the promise of the quantum computers is basically representing quantum systems on quantum computers. And Richard Feynman in the 80s, here is a famous quote about simulating quantum systems on quantum computers because it is very inefficient to do it on a classical computer. And this problem with the full configuration interaction is a perfect example of how this happens. So compared to the classical bits, which can be in state of either 1 or 0, in quantum bits, for the same number of bits, we have the same number of possible states, so a collection of zeros and ones. But now we can have a system in a superposition of these states, and we get a much more compact representation of a quantum state. And so, in general, if we want to study some quantum system, we can map the initial state of our system onto the quantum computer, then do some evolution of our system, and then map it back to the classical computer and basically get measure the state and get the properties of our real quantum system and get the solution to our problem. And essentially, when you try to represent a quantum system of 50 qubits on a classical computer, you will need 16 petabytes of storage. And basically, since it's 2 to the power of n growth, when you add extra 2 qubits, you multiply the number by a factor of 2. And that is how you get to the threshold of the classical computation. And so there are 2 types of quantum computers, analog and digital. In the analog, you map Hamiltonian of the system onto the simulator, where you can control and tune the parameters. And by tuning those parameters, you basically study the system. The example of this is the D-Wave quantum computer. And what I'm going to talk about is the digital quantum computation, where you can represent any evolution of the Hamiltonian as a set of elementary quantum gates, and just it doesn't matter what's the underlying architecture of the quantum computer. It's all digital, just like the classical computers. And when you use digital computers, you can then use some algorithms like VQE to find the solutions to the problem. So before we go to VQE, I'll briefly mention the quantum phase estimation algorithm. As I've already said, it can be used to find the eigenvalues and eigenvectors of the unitary operators. And if you have a unitary operator and you can prepare approximate eigenstate of the system, for example, for quantum chemistry, it can be a Hartree-Fock solution, which is relatively easy to do on a classical computer. Then you can use quantum phase estimation to find its eigenvalues and eigenvectors. And it has been shown over 20 years ago that if you that this algorithm gives you exponential speed up for this problem. However, there is a problem that for this method, the required quantum hardware is not kind of hardware we have today, and it'll be quite some time until we have that. So that's why the variational hybrid quantum classical algorithms emerge. And essentially, to give you an idea where we are now, if you're not familiar with that yet, here is the development roadmap for the IBM quantum hardware, where this year they are supposed to come up with a quantum computer with 433 qubits, and getting into 2025 around 4,000 qubits. And then beyond that, who knows, they adjust this roadmap every year. And basically, even the number of qubits is not that great, and that's even before we start talking about the fact that there is a lot of noise in these devices. But anyway, this is a sort of why we need more, why we can't run the real quantum algorithms just yet on quantum devices. So in variational quantum eigensolver, as I already said, it is a hybrid method where the energy of the electronic Hamiltonian is computed on a quantum computer, and we have variational parameters that are optimized on a classical computer. And the main components here are mapping of the problem onto the qubits, parameterization of the wave function, and classical optimization of energy with respect to variational parameters that's done classically. So first of all, the equation that I showed you on the first slides, the electronic Hamiltonian, it's so-called first quantized Hamiltonian, where we have one electron terms that involve one electron and the two electron term. And we're mostly working in second quantization when we run quantum chemistry problems on quantum computers, where we have the occupation number representation, where each qubit can be represented as a molecular spin orbital that can be either 0 or 1, and these creation and annihilation operators will either create an electron in a certain spin orbital or annihilate electron. And this is sort of how we map the electrons to qubits. And here are more details about that. Because electrons are indistinguishable, they need to obey Pauli principle. So we have to have wave function that's anti-symmetric with respect to exchange of two electrons, but qubits are distinguishable, and therefore it is not as straightforward as we would want it to be. The most chemically intuitive mapping, as I said, is Jordan-Wigner mapping, where we have qubit in state 0 as an unoccupied orbital and qubit in state 1 as an occupied orbital. And here is the sort of expression for how to transform electrons into electronic Hamiltonian to qubit Hamiltonian. There are other mappings, but this is Jordan-Wigner is the easiest to interpret in terms of because it uses the occupation number to represent the qubits. So, as I said, we have the electronic Hamiltonian is when we write it in second quantization, we have these one electron terms that we compute on classical computer, as well as two electron integrals. And these are creation and annihilation operators. And when we map it onto quantum computer, we, regardless of the mapping that we're using, we end up with the expression for Hamiltonian as a linear combination of these products, where these alphas depend on these electron integrals, and these sigmas are basically Pauli matrices, which are simple Pauli matrices that are right here, identity matrix and X, Y, and Z matrices. So once we're done with the mapping, so here just the example of how what it looks like when you actually start running these things in Qiskit. So we have our molecule in terms of spin orbitals, where here we have for hydrogen 2 molecule with 2 electrons in minimal basis set, we have 1 electron on alpha orbital and 1 electron on beta orbital, and the fermionic Hamiltonian looks like this, where these are coefficients that depend on the electron integrals, and these are creation and annihilation operator that create or remove electrons from a certain orbital. And once we map it onto quantum computer, you have these again linear combination of these products where we have some coefficients and the Pauli matrix is acting on certain qubits. All right, so here is the flowchart for the variational quantum eigensolver. I've talked about most of the pieces here. Basically, we start with the fermionic Hamiltonian problem, perform the Hartree-Fock solution to get the initial trial state. Then we map the problem to qubits that I've just talked before. And then we generate ansatz to represent the trial wave function. This part I'm going to talk about in a few minutes. But basically, if we start with the Hartree-Fock wave function and apply some unitary operator to it, we can represent this wave function on a quantum computer. So these are the quantum gates, and thetas are variational parameters that we're going to optimize in this classical optimization loop on a classical computer. So once we prepare this trial state and we measure all the terms in the Hamiltonian, we use the variational principle to minimize the energy with respect to these variational parameters. And so this is the part that is done on a classical device. So we have this loop where we get the energy from the quantum computer, and we update the parameters theta using some classical optimization algorithm. Then we prepare that state on a quantum computer again, measure energy, and so on and so forth until we meet some convergence criteria. So when we measure Hamiltonian, the main difference from the classical devices is that when you measure the Hamiltonian on a computer, you basically get a strings of zeros and ones. It's basically a probabilistic nature of quantum systems, where when you measure a state, it collapses to one of the possible configurations, and you need statistics to get the real energy of the system, and this procedure is called Hamiltonian averaging. So you really need to do this multiple times, and the more times you do it, the smaller the energy is. This is contrary to the deterministic classical computers, where you basically solve it once, and no matter how many times you solve it on a classical device, you'll always get the same results if everything is working properly. And in a quantum world, you need to perform multiple measurements to increase the precision. So let's talk about the variational ansatzes and how we parameterize the wave function. As I already said, we use some unitary operators to apply to initial trial Hartree-Fock state. And this can be represented by a unitary matrix of size 2 to the power of n to the power n, where n is the number of qubits. And this can be represented as a tensor product of multiple unitary operators acting on different qubits. And usually it's represented, we have a single and multi-qubit gates. They can also be parametrized or non-parametrized. And the main requirements for a good variational ansatz is that obviously they need to be as short as possible, because we have noisy quantum devices that have rather large errors. We also don't want to have too many parameters, because classical optimization can get very hard and unfeasible for a very large number of parameters. And obviously it needs to be expressible enough, so it needs to span the space which includes the solution to our problem. The first type of ansatz is so-called chemistry inspired, is the unitary coupled cluster ansatz, where basically we use a unitary version of the very common quantum chemistry method, coupled cluster with singles and doubles, where essentially we have excitation operator, exponential of the excitation operator that applied to the Hartree-Fock wave function. And this excitation operator is basically a sum of, in the case of singles and doubles, it's the sum of the singly excited configurations and doubly excited configurations. So from Hartree-Fock, we can get configurations singly excited and doubly excited. And the reason why we can't apply directly the standard coupled cluster method, because this e to the power of t operator is not unitary. However, e to the power of t minus chi dagger, which is a complex conjugate in the unitary coupled cluster, is a unitary operator, and it can be efficiently implemented on quantum computers. So the problem with this method basically is, I would say, mostly due to the fact that the electronic wave function needs to be antisymmetric, and essentially it doesn't matter which orbitals are connected in the excitation. You always have these cascades of 2-qubit gates, which are CNOT gates that connect the orbitals from VQE excited electrons to another orbitals. And basically all of them are connected through these CNOT gates. And really the problem with this is that each CNOT gate has a quite large error associated with it. So for example, this is the IBM Washington device that has 127 qubits. And this was taken from the IBM website yesterday. The average CNOT error is roughly 5%. And so the more of these gates you have in your circuit, you can imagine that it won't take a lot of CNOT gates to basically get the result that's completely nonsensical. And the goal is to reduce the number of these gates as much as possible, because single qubit gates are two orders of magnitude better in terms of errors. And basically everything is defined by CNOTs, as well as the measurement error. That's also on the order of, here it's 3%, but with the readout errors, it's easier to deal with. However, it's still quite a big problem. And so the other way to represent the variational ansatz is using so-called hardware efficient ansatz. And this was from the work in 2017 by IBM, where they came up with this hardware efficient ansatz, where you basically have these number of repeated blocks of interleaved single qubit gates and these entanglers that contain CNAT gates. And here you have basically D of these repeating layers. And then in the end, you end up with a lot less CNAT gates. However, you get quite a bit of parameters, and you have really high expressibility, or in other words, it covers a very large space of solution. However, there is a problem with this approach, is that there is no chemistry involved in this. This is just sort of a random combination of gates that can represent a lot of relevant and irrelevant to chemistry states. And you need to do extra work to enforce basically the symmetries that come from the chemistry or physics domain. And essentially, what this picture here demonstrates is that when you use this hardware efficient ansatz and you have two solutions, A and B, and your ansatz covers some accessible space, you have a certain landscape for finding where your solution lies. And once you start increasing this accessible space, you get to the point where when you try to minimize the energy, you run into a problem that your solution line is very narrow sort of space where you have non-zero gradient, and that's the famous problem of barren plateaus, where a couple of years ago it was demonstrated that when you start increasing the size of the system, so the number of qubits, the variance of the gradients decays exponentially, and that's for random circuits. And hardware efficient ansatz is basically a random circuit in a sense. And what we're getting basically is that if you start if you don't start somewhere in a region where you have non-zero gradient, you're basically doomed to find the real solution, because when you compute the gradient, it's essentially zero everywhere except for the shallow region where your solution lies. And that comes from the fact that there's no really chemistry in the representation of in these hardware efficient ansatzes, and the space that it covers is very, very large. However, they did do some simulations on hardware because they don't have that many CNAT gates. And this was done on IBM devices. These are potential energy surfaces of molecules H2 and lithium H. And essentially, these dashed lines are the exact solutions for the energies. And here the green is the mitigated, so which means that they used some error mitigation strategies to improve the accuracy. And you can see that without it, they are quite far from the real solution. And if you remember, when I talked about chemical accuracy, the goal is to be within 1 kilocalorie per mole, or 1.6 millihartree per mole. So this is 1 millihartree here, and essentially for some distances they are very, very far off. And this is hydrogen molecule, the smallest molecule you can come up with. And a couple of years later, they did a slightly larger molecule, lithium H, and again, the errors are on the order of tens of millihards rate. So there's still a good way to go, but these are proof of principle simulations, really, and with improving hardware, these errors are going to go down. And just sort of a quick overview of what has been done to date on real quantum hardware. And these are basically different experiments. And as you can see, number of qubits. It's mostly in just a few, 2, 4, 6. In the study on 12, they did Hartree Fox, so this is not really comparable to the other studies, but that's basically the state of the art nowadays. So most of the research is done for not computers that are available today, but for the future. And to summarize, we basically have the chemistry-inspired ansatz, which has less variational parameters, easier to interpret. We have enforced physical symmetries. We only get the solutions that are chemically valid. However, the circuits that they produce are very, very long. And for realistic systems, they're not doable on modern hardware. Whereas in hardware efficient ansatz, they are easier to run and more expressible, but they can be really inefficient, and you can have these problems with symmetries of the system, which are hard to enforce in some cases, and the Baring-Potel problem that I've talked about. So to summarize, variational quantum eigensolver is an alternative to the fully quantum phase estimation algorithm for the near intermediate scale quantum era, where our computers today are very noisy, and we try to limit the length of the circuit that we run. And essentially nowadays, modern computers are not, quantum computers are not good enough to run problems that cannot be solved classically on the modern classical computers, and that's it's related to this idea of quantum advantage, where you can use a quantum computer to solve some useful problem that cannot be solved classically, and that's what everyone's goal is, really. And for the variational quantum eigensolver, in terms of ansatzes, to do it more efficiently, we need to reduce the circuit depth in chemistry-inspired ansatzes, and for hardware-efficient ansatzes, the goal is to reduce the number of parameters, which tend to be really large. And I would be happy to answer any questions that you have. All right, I don't see any questions in the chat, so if you have a question, feel free to unmute yourself and ask your questions.
Hello. Hi, I had a quick question.
Yeah.
So in these hybrid algorithms, right? So the optimization part is still done on classical hardware, right? And I was wondering, so you were talking about Baron plateaus. So these are pretty much gradient-based optimization schemes, right? Is there any interest on can you comment a little bit on if like global optimizers which are gradient free can be applied to such problems?
Yeah, there is you can apply various optimizers the sort of the main issue with it's a whole another field, classical optimization. I can just say that the main issue with the optimizing of these of doing classical optimization for this variational quantum algorithm is that you get a good amount of noise, and so essentially you have high error rates, and if your energy is off, your gradient is also off, and therefore for a lot of optimizers they really struggle with doing this optimization in this environment where you're not really sure how in your gradient value, and so a lot of them would just struggle. And there are certain algorithm like stochastic optimization algorithms that are better suited for this. But yeah, this is with increasing size of a system, it can become really problematic, especially with noise. But even without noise, these tend to be non-convex surfaces where you have plenty of local minima, and you can. There's a very high chance you will get stuck in one of them. So you need to sample different
Just
points.
okay, thank you. And just to follow up on this, so
Yeah.
is there like a optimizer that people use? Like, is there like a standard for such problems in quantum computing?
Yeah, I'll actually talk about those a little bit in the hands-on section. We will run some optimization, VQE optimization using noise, and I'll talk about those, yeah, in the next
Okay,
hour.
awesome. Thank you very much.
Any other questions?
Hi, Dmitry. Nice presentation. So it seems to me what the main issue with the unitary Kapov cluster is this type of sort of mapping is the anti-symmetry, right? So the wave function, that's what results in a long circuit, I think, right?
Yeah.
So that sounds pretty much the same as an representability problem in density matrix theory, right? So because you basically working in a occupation number sort of picture, which is effectively a density matrix.
Yeah.
So I'm just curious. So is anybody try to actually, so there is an opportunity here from sort of qubits point of view. Is anybody try to implement the system of qubits where qubits actually antisymmetric? Let's say like there is an array of like spins, right? Which are actually satisfy antisymmetry requirements, like arranged on a lattice or something like that. That's what sort of already put this what you call chemical sort of restriction on the qubits themselves, and that might sort of simplify algorithm significantly, or at least reduce the number of gates you need, right? So
yeah, so it's an interesting idea. So I've never heard of anyone actually trying this. I think ultimately it's just quantum chemistry is just one of the problems they can solve, and nobody thought of sort of building this hardware specifically for this kind of problems. But I think it should be possible.
Yeah, it's kind of pushing this towards the analog quantum computers, right? But it's still not really analog. You still use sort of the gates and stuff. It's just very restrictive gates. So
yeah, that's an interesting idea.
Yeah. Okay. All right. So yeah, I'm just curious if anybody, like, if you saw anybody publishing something on that or something.
Anything like that.
All right. Okay. Well, thanks.
Of course. Any other questions? All right. So we can switch to the hands-on now. So as Yuri mentioned, we will need the, so first of all, you will need IBM Q account to run this, which is super easy to get. I'll share my screen again. So if you go to IBM website, which I'm gonna put in a chat. So on this website, as soon as you register, which is it only takes like 1 minute probably, you will well, actually I can sign out and show you. So on this quantum computing IBM.com, you will see this sign in here, and here you can create an account. Basically go through this process. It will just send you an email and you need to confirm. And once you're in, what we'll be using is this IBM Quantum Lab over here. So now you have a couple minutes to go through this process if you haven't done so yet. And when you launch this Quantum Lab, it is basically the environment where you can run the Jupyter Python Jupyter notebooks with tutorials. So you will need to download the on this GitHub page that I'll also post to the chat. So it is in the chat. If you go to this GitHub page, you can download the this repository, where you click on this green code button and then just download the zip file. And then you simply unpack the zip file, and you then go back to this IBM Quantum Lab and click Upload Files, and pick the file, the folder that you downloaded from the GitHub. And it has, I think it has these 4 Jupyter notebooks. And yeah, now we can have a, I can wait a couple minutes until everybody is at the same page. If you need any help, just you can ask in the chat, or you can unmute yourself and ask your questions, or any questions related to the presentation as well. And we can start in a few minutes once everyone's ready. All right. I think I'm going to start, and this will be available afterwards. And Qiskit has it's a quite popular package, and there is plenty of different tutorials and different notebooks and different algorithms, and it has a really nice it's called Qiskit textbooks, that basically a introduction to quantum computing and how to do it in Qiskit. But let's begin with our VQE problems. And the first notebook, which is called Qubit Hamiltonian. And I'm gonna do this. All right, so hopefully everybody can see this. We begin again, as I was explaining, with the molecular Hamiltonian and use the Born-Oppenheimer approximation to separate nuclear and electronic degrees of freedom, which brings us to the electronic Hamiltonian problem. And we use the we use the variational principle to find, to do classical optimization and compute this energy of the ground state. So with the initial state, again, we do the Hartree-Fock calculation on a classical computer and compute these 1 electron integrals and 2 electron integrals. And that's done prior to the calculation on the actual quantum devices. And that's done, that can be also done with the multiple quantum chemistry packages that are, so one of these basically, but I'm going to use the PySCF. And before you start, you should run this command basically to install the PySCF package. I'm not sure why it's not a part of the environment already, but nevertheless, run that. It will install the PySCF package in this Python environment that you're working in here. And we begin with importing this PySCF driver, which does the Hartree-Fock on a classical device for the molecule that we specify here. So it's a simple H2 molecule. And in the PySCF driver, we use as input the molecule, units in angstroms, and the basis set, this STO3G is the minimal basis set, where you have a single basis function for every orbital. And after we are done with running the classical part in the PySCF, so hopefully you don't run into any issues. After we do the Hartree-Fock, as I was talking in my presentation, we need to map our classical electronic Hamiltonian from fermions to qubits. So there are, I would say, 3 most common ways to do this mapping. So Jordan-Wigner, parity, and Bravik-Kitaev mappings. The most chemically intuitive is the Jordan-Wigner mapping, as as I told you in my presentation, where you basically map the spin orbital occupation onto the qubit. And this is what we're going to use here. So here we just load the all the modules that we need. Sorry, this is repeated from the previous one, but here we use the electronic structure problem that we import here, which basically sets up the whole problem for the current driver, BiSTF driver that we specified. So basic molecule, basis set, the charge of molecule, multiplicity. This is the structure that you use for solving this problem. And if you call the second QOpt on this electronic structure problem, what you will get is the second quantized Hamiltonian in the occupation number representation. So if you print second QOpt, it will give you, well, this is not a very nice representation. It's essentially, as I was saying, it's these creation and annihilation operators and the corresponding coefficients in front of those. And after we do our mapping using the Jordan-Wigner transformation, so that's what we do in this cell here, where we use the qubit converter with the Jordan-Wigner wrapper to get the our qubit Hamiltonian, which is over here. It's basically, again, as I've shown you in the presentation, we have the coefficients and the strings of these poly matrices, and the number of these poly matrices is equal to number of qubits, where they can be X, Y, Z, or I, which is identity, which means nothing happens on that qubit. Again, we can use different mappers. It will still be the same dimensionality, but you will get different combinations of matrices. There is also this the trick that is can be used for considering the size of the inequality of modern quantum hardware. This ends up being quite a useful trick to basically use the symmetries of the molecule to reduce the size of a problem by 2 qubits by taking advantage of how the symmetry is stored there. So if you use this 2 qubit reduction flag, it reduces the number of the qubits required to represent the problem by 2 qubits. And this qubit Hamiltonian over here is the same as this one. It just represented in a compact way where you take advantage of the symmetry. And obviously this is for small systems where 2 qubits is a big deal, like in this case. Going from 4 to 2 is more exciting than going from 100 to 98. And here it does make a difference, and That's just the thing that you can do here to slightly reduce the size of the system. Are there any questions on the mapping of fermions to qubits? Did everyone get this working? Yeah, feel free to put it in the chat or unmute yourself. And at any point, if something is not clear, I'm happy to pause and explain this in more detail. If there are no questions here, I'll move to the second notebook. Is the that's called VQE state vector. So we don't need this here. So again, we here we just load all the needed functions that we're going to use. But here we will actually run the actual VQE calculation on a simulator, not on a quantum computer, but on a simulator. So here again, up to at this point, we're basically doing the same thing as in the previous notebook. We essentially run the classical Hartree-Fock calculation, set everything up for our computation, VQE computation on quantum hardware. And this is the Hamiltonian that I'm going to work with here. Before we go to the VQE, it is nice to have the sort of the exact solution to a problem. And for these small problems, we can just simply diagonalize the Hamiltonian. You find the exact solution for given basis set. And in this cell, what we're doing is we're using this NumPy minimum eigensolver that diagonalizes the matrices exactly. And here we use our qubit Hamiltonian as an input, and we simply run this and get the exact value of the energy, ground state energy in Hartree. So going to
excuse me, Dimitri.
I have a question here. Yeah.
Yes, you have a couple questions in the chat.
Yeah. So the first questions, what are the factors in front of the Pauli matrices? So the factors, those are coefficients that you get. I'll share my presentation real quick. Okay, I'm gonna stop sharing this and share presentation again. So here, as I was explaining this, so this is the Hamiltonian and second quantized form. This is the fermionic Hamiltonian over here. Oh, sorry. And these are 1 and 2 electron integrals that you compute on classical computer. So when you do the Jordan-Wigner mapping or any other mapping, you end up with this linear combination of the Pauli matrices with these coefficients, where these alphas basically depend on these 1 and 2 electron integrals. They are defined by these values. Basically, you just do the mapping, and it's some coefficient that depends on these two. Depending on the mapping, it will be slightly different, but it's not 1-to-1 correspondence. They are different coefficients. And the second question is, what do the ops in the second QAOA array represent? So the operators, so here on this slide, so on the left, you have a fermionic Hamiltonian, and you have spin orbitals labeled as 0, 1, 2, 3 if you start indexing from 0. And so, for example, if you look at the first term over here, you have A0, which this is annihilation operator. So it annihilates this electron, so it removes it from this orbital. The second operator creates electron on orbital 1. So these first two operators, they essentially move this electron from 0 to 1. And the second one does the same thing with the 2, 3. So this first term represents the double excitation where this electron goes from 0 to 1 and this electron goes from 2 to 3. And just keep in mind that there are two sort of more common, like in quantum chemistry, you're mostly looking at these spatial orbitals that only that can have 2 electrons, alpha and beta on them. But here it's more convenient to work with the spin orbitals, where you can have 1 electron on 1 spin orbital, basically. It is obviously easier to map onto qubits, because qubits, you can only have 0, 1 for 1 qubit, right? So this first term is basically the double excitation that I was talking about. And after you do the transformation to qubits, this gets less intuitive, but for example, on this first, the first term here, it's just a bunch of the identity matrices. So basically nothing, it's just a coefficient here. With the second term, you apply Z matrix on this third qubit. So another question, second QAOA 0 seems to have multiple terms. So these multiple terms are the terms of the Hamiltonian. So in this case, it is 15 over here. It's essentially 2 to the power of n in the Hilbert space, where n is the number of qubits. So what really is happening here, we just simply go from using these fermionic excitation operators in the second quantized form, meaning that you work with the occupation number representation as 0, 1 for each spin orbital. You go to the quantum computer where you have also basically 0, 1 representation, and this is how these two are related. All right. And yes, another question, looks like rotating wave approximation is implied here. Yeah, could you elaborate on that question regarding the rotating wave approximation, if you can unmute yourself? I'm gonna switch back to the notebook. Oh, you're asking if you don't have terms such as AA or A dagger and A dagger. Well, essentially, you get all the possible states that you can get. So you have to preserve the number of electrons, and that's why you don't just annihilate all your electrons and end up with a molecule without any electrons. All right, so going back to the our notebook, we have the qubit Hamiltonian, and we solved it exactly. We got some energy, and now we can talk about variational ansatz. So I'll start with the unitary couple cluster. And here we need to provide initial state, which is basically the Hartree-Fock for certain number of spin orbitals, number of particles, and then we use this UCC class here, where we provide the number of spin orbitals, number of particles, the converter, which is our Jordan-Wigner mapping, and the level of excitations, which I've talked about. We only, to reduce the cost, we only look at singles and doubles. So we only consider single and double excitations. But in principle, nothing stops you from doing higher order. You can do in triple and quadruple. However, those are very, very expensive things to implement. And not only each of them is more expensive to implement in terms of gates, there is also a much larger number of them. So it just kills you very quickly in the sense that you can only do rather small systems. And essentially, here I just print out this ansatz after Qiskit builds it. So for our H2 molecule, you get basically ansatz with 3 operators, and if you use this decompose function on this ansatz, it will print you something like this, which has these Hadamard gate and the not Hadamard gate, the X gate, which is basically this basically represents Hartree-Fock, where it puts it flips from 0 to 1 for your electrons. This is less intuitive than looking at the 4-qubit problem because we reduced it using symmetry. It's less intuitive, but that's basically what Hartree-Fock does. It puts some electrons on the lower orbitals. And then we have 3 operators. These are basically excitation operators. And it's not intuitive how we got to these from the fermionic ones, but that's basically, if you do the math with Jordan-Wigner, you can arrive at these gates, and you can further decompose this into I haven't found a better way to do this. They, for some reason, insist on decomposing one level at a time. But eventually you will start getting into more elementary gates that are actually implemented on the hardware. So here you have some use our rotational gates in X, Y, and Z. U1 is the rotation on one axis, and these are CNAT gates over here, the 2-qubit gates. And basically, you can play around with this and see what the circuit actually looks like. So that's no questions regarding this. When you try to use the hardware efficient ansatz that I was talking about, which is, as I said, it's a lot simpler, and really there is no strict rules on what will go inside of them. It just sort of works for small systems, but I'm really not sort of optimistic on how useful this can be for large systems, just for the reasons that there is no domain knowledge from your system in these circuits, and it can be quite challenging to converge to some solution. And as you can see, this only has a couple of rotational gates and a couple of CNET gates, and it's a lot easier to run. Here we can start with the actual VQE calculation, for which we need to specify our variational ansatz, which we defined over here. So for hardware efficient ansatz, we basically tell it what kind of rotational gates we're going to use, what kind of entanglement gates we use, in this case is CZ, and how many qubits. And going back to VQE, after we specify the ansatz, we give it the optimization algorithm. So for classical optimization, in this case, it's BFGS method. And also you need to specify the backend for the simulation. So backend could be a quantum computer, the actual quantum device that you can actually try for yourself. IBM has a couple of machines that are available for everybody. But in this case, we start with the state vector simulator. And essentially, state vector simulator, what it does is it represents everything in terms of every operator in terms of a matrix. Like unitary operator can be represented as a matrix. And what it does, it's basically doing this deterministic calculation where you will get in the end your wave function. If you start from the Hartree-Fock and you apply a bunch of unitary operators, you will arrive at your solution. Whereas in the real quantum hardware, you get a state of a system that collapses to one of the possible configurations, and then you have to average. So in a sense, this gives you a sort of exact solution for this particular ansatz that you chose, which doesn't mean that it's going to be close to the real solution, obviously. But anyway, if you run this, it will run very quickly because these matrices are of dimensionality 2 by 2. And what you get in the end is basically some information about the optimization, how many evaluations did it do, what's the eigenvalue, and the optimal parameters over here. And this is the hardware efficient ansatz. And you can compare this value 1.85727 to our exact solution, and it is quite close to what we got here, but it's also a very, very small problem, so that is not surprising. And if you run with unitary coupled cluster, so we do the same thing, we just replace hardware efficient ansatz in this VQE structure by the unitary coupled cluster ansatz. and the rest stays the same. And here again we get the result of the optimization. It took much less iterations, so only 20 evaluations. It got us the same result, and we only have here 3 parameters, and actually 2 of them are actually 0. There is this brilliant theorem that tells you that these single excitations in this molecule are forbidden, and you only really have 1 double excitation, and really all you need to do to describe the H2 molecule on a minimal basis set using unitary coupled cluster with single and doubles is only 1 double excitation. That's the only possible excited state configuration here. And this is one of the other things, how you can reduce the circuit length and depth is by using the knowledge that you get from about the molecule. So the symmetries, if some of the excitations are forbidden, you can simply remove these blocks, these excitations and the corresponding gates from the circuit, and you will get the same answer, but with a shorter circuit. And so the bottom line so far here is that unitary coupled cluster uses realistically here only 1 excitation operator, and it converges much faster, whereas the harder efficient ansatz, it has less CNOTs, but it has a lot more parameters. And you really cannot use any sort of tricks with the like I just described with the unitary coupled cluster. When you know the symmetry of a molecule, you can throw out some of the excitations because none of it is based on chemistry. So and quite arbitrary how you do it. And if you are interested how your simulations converge, you can use this callback function to store the intermediate values during the optimization. So here is the this callback function that stores that data for you, and in the end you can run basically multiple use optimal optimizers. So in this case these are Cobila, BFGS, and this stochastic optimizer that is good for noisy environments. And so here it's already finished with simulation, and we can plot the result for these 3 optimizers. I'm not sure what's going on with the labels here. It's all blacked out, but essentially on the bottom here is the number of iterations, and on the y-axis it's the energy. And you can see they are they're all of for this particular problem, they are they give you comparable results, and maybe Cobila converges maybe a little faster to some point. Any questions so far? Feel free to type them into chat. So is it just the same? Yeah, we can move. If there are no more questions, we can move to the simulation with noise, which is notebook 3 in those files. As I mentioned before, this state vector simulator simply multiplies these unitary matrices and gets you deterministic solution if you start from the same initial point, obviously. Because as I said, the classical optimization can converge to local minima. And obviously, if you start from a different point, you might get a different result. But the point is that if all the inputs are the same, you will get the same result. And here we're going to use this Qiskit air simulator, which is basically simulates the quantum measurement process, where instead of the sort of wave function vector that you get from the state vector, you get array of zeros and ones, and you have to run that multiple times and average and get the statistics to get the wave function. So again, we begin with loading all the necessary functions. To make it easier, I just copied the actual operator from the previous notebook. The same thing with the exact solution. We simply diagonalize the matrix and get the result. Another important thing that you get when running the quantum measurements, there are two types of noise when you do these quantum measurements. The first kind is the statistical noise, where when you measure a state, it collapses to one of the possible configurations. And that would happen even if your hardware was perfect with no errors whatsoever. You would still get the distribution of the result, and the average would be at the real ground state. And that does not include the noise that comes from the quantum hardware, where essentially you get errors on top of the statistical errors due to the imperfections in the hardware. And we will begin with first with just statistical noise here. And if you run it, you will notice that it is taking much longer, because it needs to run many repetitions, and you obviously, the more repetitions you do, the higher precision is going to be. And if we wait until it finishes we can compare the numbers for noiseless simulation and in the simulation with noise. Yeah, so it just finished here in this chasm simulator. It's what IBM calls this simulator in Qiskit. So without noise, it gave us this energy, which is higher by this number in Hartree from the reference from the exact value. And if we plot this, you can see that you get this a lot of these statistical noise that complicates the optimization process, because when you have this uncertainty in energy, you'll end up running it for longer to get to the accurate values. And now we can add the noise to the simulations. To make it simpler, instead of using the real quantum hardware, IBM has these mock backends which mimic the noise that you would get from real hardware, but without actually using the real hardware. And in here we import this fake video device, which we're going to use for the simulation. And yeah, basically doing the same thing with just with noise now. And it will take even longer than it did before, because the amount of noise is going to increase, and it'll be visible on the graphs that I'm going to show you. And here it just prints you the noise model, and that's basically information for more for experts what's going on there under the hood. And when it finishes, it will basically you will get something like this, which is similar to what we saw here for the just statistical noise case, but it takes the more noise you have, obviously, the longer on average it's going to take. But here, really, what I wanted to point out in this notebook is the 3 cases how you can do your simulations. It's the state vector, where you get the exact deterministic result, and QASM simulator without hardware noise, and QASM simulator with noise, which is also, you can run it on the real hardware and you get also both types of noise there. And here you can see delta from the reference energy with noise is now 0.05, and it was 0.004. So you get basically more error, which is not surprising. And there are strategies how you can mitigate the noise, which is quite complex, complicated area, and there's a good amount of work done with it in it. But basically, you can, knowing that you have, for some errors, you can have strategies that will sort of not get rid of the error, but get rid some of the error and make result more accurate. And the question from the chat is, if can we define noise level in terms of qubit properties such as T1 and T2? Yes, those are the main components of any noise model. That's yeah, that's really how you define it. in simple terms, there's more to it than T1 and T2. There can be coherent and decoherent noise, and I don't want to get into these tiny details, but the simple answer is that yeah, the T1 and T2 times are the main properties of a device that define what sort of error you will get. Why does the convergent energy I have that particular shape on the graph started in some medium value, then increasing to some peak, then falling?
Maybe I can add to that. What question is that probably the best way to do it is to take one of his IBM fake, right, quantum devices, right, and you can actually, I think you can modify T1, T2 connectivity and all these characteristics.
Yeah,
right? That's basically the way to go if you want to modify it. And I think there's a second question, Dmitry.
I was just starting to read it. So basically, the question is why the energy, when it is converging, why it jumps to some peak and then goes down again. So this is precisely due to the noise, because we don't. You have some uncertainty at each iteration where you can end up in terms of energy. So. And that is the challenge for classical optimization that I was talking about, because you don't just get a certain energy for a certain point in your optimization. If you run it multiple times, you can always get slightly different answer. And this is basically what this represents. That's the noise, and you can see this long stretch. It converged to some sort of average value, and then it continued with these oscillations until it just stopped, because with this number of measurements for each term, number of repetitions of the same circuit, this is kind of uncertainty you're getting. Basically, to smooth this out, it's definitely helpful to increase the number of measurements. However, it is obviously expensive to rerun everything many times, and it was on my slides. The sort of the convergence. The precision scales as 1 over epsilon squared, meaning that if you want to achieve precision epsilon, you will need the number of measurements that scales as asymptotically scales as 1 over that precision squared. And to put this into perspective of what the numbers are we talking about, for chemical accuracy, which is 1 millihartree, which is 10 to the minus 3 hartree. You square that, you get 10 to the minus 6, and that gives you rough estimate for the number of measurements you need to do for each circuit, which is basically, for chemical accuracy, you basically need million measurements. Here, I think the default is 1,000, and this is what you get, really, 3 millihartree, which is higher than chemical accuracy, and that is hydrogen 2 molecule that is literally the smallest chemical system you can come up with, and is not obviously an issue for any classical algorithm. But at the state of the quantum devices, that's sort of you, and regardless of the state of the devices, even on more sophisticated hardware of the future, you would still need this number of measurements to get to this accuracy, because in this case, yeah, I was talking about this number where we only use statistical noise. We only have statistical noise, so it is 4 millihertz error here. Even for this, this 1,000 measurements is not enough. You need to do more to get to the chemical accuracy.
Yeah, so maybe I will just summarize that. So the chemical, quantum noise makes a huge impact on the convergence. So what noise does, it essentially flattens potential energy surface, right? And what it makes, and also it reduces some artifacts. And what it does, it basically, it makes convergence time consuming, right? And if it's not like something is not done correctly, if not enough, and it will actually may lead you to wrong converged value as well. So that's basically, and that graphs, these graphs what actually Dmitry is showing, were basically kind of like show we struggle, right? We converger optimizer.
Yeah, so the as I was saying, if you take sort of a single piece of information out of the presentation, it should be the sort of the main difference between the different between the classical computation and the quantum computation is that quantum measurements are statistical measurements, and you don't get your wave function at the end of a quantum circuit. You only get a possible solution, and if you average that, it's going to be centered at the real, not the real, at what the state vector simulator would give you that works with the matrices that gives you a deterministic answer. And two types of noise: statistical, just from the simple fact of measurement, and hardware noise. And as I've shown you in the presentation, the noise for the double for the CNOT gates, which are 2-qubit gates, is on the order of a few percent. And this is obviously not scalable with these numbers. They're simply too high to run anything very long. So the sort of the main struggle of the quantum hardware, I would say, is not the number of qubits that everybody likes to talk about, because even with 100 qubits, I'm sure if those were high quality qubits with low error rates, there certainly would be some problem, an algorithm that would show the advantage of the quantum algorithms, because the threshold for simulation of quantum problems on classical computers is roughly at 50 qubits in that area, depending on the size of your computer. And essentially, you cannot even put the general quantum state on a classical computer with more than like 50 something qubits, because it's like petabytes of information. And then again, you need to run an algorithm on it. And so with 100 perfect qubits, you would certainly be able to do something useful with it. The problem is that is in a sort of in a general, what comes to the general public is mostly the number of qubits, and the reality is that it's just a part of the problem. it's not enough to get a big quantum computer. You need it to be very less error prone. And I think that is it from me. If you have other questions for me, I'd be happy to answer them. And maybe Yuri have some other things to add.
No, it was great. Yeah, so yeah, and this problem of noise, right, is called Baron plateau problem, right? You can find plenty of papers on this subject.
Yeah, so most of the research, obviously there are algorithms that theoretically were shown to have advantage, and it will, I think, happen at some point, but it's not today or tomorrow or next year. This is all work for the future hardware devices. This is all very exciting and fundamentally different from classical computation. As I said, it's not just the faster computers solving the same problems. It's a different approach. And obviously, the most sort of straightforward thing is when you simulate quantum system on a quantum computer. It's like a natural thing, but also there are applications that some clever algorithms that take advantage of quantum effects to solve classical problems, such as like optimization algorithms. And you will hear more about that this week.
Yes, maybe just to finish it, Dmitry, maybe you can summarize like why it will be hard to actually achieve quantum advantage, right, of VQE with particular quantum algorithms. I'm talking about issues with depth, right? Also with number of parameters, right?
Yeah.
And so
on. Yeah. So the not to shoot ourselves in the foot by saying this, but it's generally hard to extrapolate sort of how hard these VQE simulations will be in reality, but it really is. It does get much more complicated. So if you talk about the, I'll bring up the representation again, and in particular the unitary couple cluster here. So when you have a large system, the number of these, so this is the excitation operator that constructs your ansatz, and here are the single and double excitations. So asymptotically, the number of these double excitations increases as n to the power of 4, where n is the number of qubits. And basically, for a large system, say with 100 qubits, you're going to have 10 to the power of 7 of these excitations. And so will be the number of parameters. And really, this on top of the fact that you will need to put this on a quantum circuit, and each excitation is this scary thing with the number of CNOTs equal to 2n. So you'll get long circuits that are hard to implement in hardware because these CNOTs tend to have larger errors than single qubit gates. You also run into a problem of optimizing all those parameters. So, and I want to remind you that also the potential, the surfaces you optimize on can be also non-convex. And there's problems with local minima and the problems with noise and number of parameters. And the hope is that this is somehow will be useful in some maybe other way, but certainly scalability of this to sort of real problems that can be solved in classical hardware is there needs to be some more to it than it is in the current form, I would say. I think there is another question. Has there been research in using Qiskit for modeling decoherence? Is that something, you know, people tried? Yeah, so I think, yeah, there's plenty of research in the field of error mitigation and noise models, and how it affects the sort of how your algorithms perform, and performance that depends on these T1 and T2 times that basically the metrics that people use for to describe the quality of the hardware. Yes, it is a very there's a lot of research going on in the field, simply because it is the main issue with the hardware. And you need to, first of all, you need to learn how to improve the hardware, but also you need to know how does that noise affect your results. So yeah, it is a very there's a lot of research going on in that field. All right. Anything else?
Yeah, we are almost out of time. So if you have more questions, maybe you can ask Dmitry. Dmitry, can you write down in the chat your email? So people can ask you directly questions. But thank you very much, Dmitry. Very nice presentation. Yes, here's the email. You can see in the chat. So with that, we are actually done for today. So we'll continue tomorrow. Tomorrow, again, at the same time, 10 a.m. And tomorrow, we're going to talk Ruslan Shaidulin. He's now working at JP Morgan. He will actually talk about how to solve optimization problems using QAOA algorithm. It's a quantum approximate optimization algorithm. So we'll continue tomorrow at 10 a.m. Central. Okay, so thank you, everybody. Sue, please stop recording.